Welcome back to the class on power semiconductor, right? In this lecture, we are going to discuss about the variable frequency control of three-phase induction motor. Variable frequency control of three-phase induction motor below the rated speed. Here, we are going to study in two different cases. One is below the rated speed and above the rated speed. In this method, we know the synchronous speed of induction motor Ns equal to 120 f/. So, the number of poles is constant. If you increase the frequency, the synchronous speed of a motor also will be increased, and the speed of a motor also will be increased. We know that flux is directly proportional to the V by F. If F is increases, the flux will be decreases. Once the flux is decreases, the maximum torque developed in induction motor will be decreases. Because we can't maintain the V by F ratio as a constant as the frequency increases. Second case, the frequency decreases, the synchronous speed also will be decreases from the above expression, and actual speed of the motor also will be decreases, but the flux will be increased. The flux is increases, more number of core losses will be occurs in induction motor. The efficiency of the induction motor will be decreases. Moreover, induction motor also will be. So to run the motor below the base speed, and to maintain the V by F ratio as a constant. If we maintain the V by F ratio is constant below the base speed, the maximum torque developed in induction motor will be same. That we are going to see now. We know that the maximum torque developed in induction motor T maximum equal to 3 by 2 omega ns into V square by Rs plus or minus square root of R square plus XS plus XR dash whole square. Plus is for the motoring operation, whereas the minus for the braking operation. The denominator, we have taken the common F, nothing but a supply frequency. Xs equal to 2 by Fs into Ls. XR dash equal to 2 by Fs into Lr. Where Ls is nothing but a stator inductance. Lr dash is nothing but a rotor inductance with respect to the stator. These two quantities are function of a F. Now take their common here, the denominator. Omega ms, that we can write it as a 2 pi Fs. So when you take the F common here F is there, Fs is there. So in the denominator we can find the F scale. That we're bringing to the numerator. That we can see in the equation. This is the equation which is deduced from this equation, first equation. Now we are going to control the speed of induction motor below the base. Base speed is nothing but suppose if we take the rated frequency is a Fs. See here we have taken the 50 Hz. Now we want to run the speed of induction motor below the base speed. So now applied frequency, you have to take it as a 40 Hz. So whenever we apply the 40 Hz frequency of voltage to stator of induction motor, the synchronous speed will be decreases. The speed of the motor also will be decreases. Now here in the denominator, Rs by Fs, we can neglect when compared to the 4 F square into Ls plus Lr dash force. Then we are getting the resultant equation V by 2 pi into V by F whole square divided by 2 pi into Ls plus Lr dash. If we maintain the V by F ratio is constant, then the maximum torque developed in induction motor also will be constant. That is happened if the speed of the motor is just below the rated speed. Suppose the frequency, if you apply the 10 Hz, nothing but we want to run the motor at a very low speed. At this case, we can't neglect Rs by Fs. It has some value when compared to this. So at low speeds of induction motor, when you are not neglecting this term, during motoring operation, the flux is there, so the denominator will be increased, the maximum torque will be decreased. During braking operation, because of minus, the denominator term will be decreased, the maximum torque will be increased. To avoid that one, at low speed, to maintain the V by F ratio is more. So that if you maintain like that, the maximum torque development in an induction motor during motoring is constant, but during the braking, the maximum torque development in induction motor at low speeds will be increased. So how we are going to maintain the more value? Suppose if we take up to the 20 hertz frequency, up to this range, 50 to 25. We are assuming that this frequency is near to the rated frequency. In this range, if we maintain the V by F ratio is 1.2. Now, from 10 ahead, you have to maintain V by F ratio as 2. Nothing but the variation of the F and is not proportional to the V at low frequency. In that manner, you have to maintain when the induction motor want to run very low, so that the maximum torque developed induction motor during the motoring operation, we can maintain the constant. Suppose if you want to run the motor above the rated speed, you have to make the voltage applied to the induction motor is constant, because we can't increase the voltage more than the rated value, and increase the frequency. As the frequency increases, the numerator term will be decreases, so the maximum torque developed in induction motor will be decreases. Slip torque characteristics of a three-phase induction motor with the V by F control. On the x-axis we have taken the torque, on the y-axis we have taken the slip. This is the maximum positive torque developed in an induction motor. This is the maximum negative torque developed in induction motor. These are speed torque characteristics of induction motor at a rated frequency. From this point to this point, this is unstable region. We are not represented as unstable region of a motoring operation as well as braking operation. This is the characteristics of induction motor during the braking. Again, this is unstable region. We always operate the induction motor between the synchronous speed to the maximum torque developed in the induction motor. Suppose we want to run the induction motor below the base speed and reduce the voltage so that V by F ratio is constant. So the maximum torque developed in induction motor will be same during the motoring operation as well as the regenerative operation. If further decreases, you get the same profile, but the same graph will be shifted downwards. The maximum torque during the motoring as well as the braking also the constant. Suppose if you want to run the motor very low value, the maximum torque developed in induction motor will be the same, but during the braking, the maximum torque developed in induction motor will be increases because we increase the V by F ratio. If further decreases, suppose if you want to run motor very low speeds, then you have to increase the V by F ratio, which affecting the maximum torque developed in induction motor during the braking, but in motoring it is a constant. Suppose if you want to run the motor above the base speed, then you have to increase the frequency at a rated voltage. So the maximum torque developed in induction motor during the motoring as well as the braking also will be decreased. If further increasing the frequency, this is the characteristics of motoring. For decreasing the maximum torque during the motoring operation as well as the braking operation. Further increasing the frequency, again the maximum torque will be further decreased. In this manner, we got the group of slip torque characteristics of induction motor at a different frequencies, where the frequency will be changing from the 0 to the above rated value. Variation of voltage at frequency. Now take the frequency on the x-axis, voltage on the y-axis. This is the variation of the voltage up to the rated frequency. This is the rated frequency. Once the frequency is reached the rated frequency, after that the voltage is constant. This is a constant. Why this graph is starting from this value means at a low frequencies, nothing but at low speeds of induction motor, we are maintaining the V by F ratio is more than the frequency which is near to the rated frequency. V by F control of a induction motor has a lot of advantages. Speed control of braking is available 0 speed to the above rated speed. The transition operation can be carried out at a maximum torque with a low stator current. The copper loss will be decreases, efficiency of the induction motor will be increases. The power factor also will be increases because we are restricted to operate the induction motor between the synchronous speed to the maximum torque condition. Drop in speed from no load to the full load is low. This is the variable frequency block diagram. So this is the delay block. This is the flux control block. This is VF, VS, nothing but a variable frequency, variable voltage source. This converter may be the inverter or the cyclone converter. This is a three-phase induction motor. This is the DC supply. How much frequency you have to apply here, depending upon the how much speed we are rotating in the induction motor. Suppose initially if we take the 40 hertz frequency, here if we take the 40 hertz frequency, due to the delay block, now the frequency will be changing from 0 to the 40 in this manner. Slowly it will be changing. This is 40 hertz. If the frequency suddenly changes means the motor may not be track the synchronous speed. So here we kept the delay block. So whenever we kept the delay block, the frequency will be slowly changes. Same signal is given to the flux controller. See, the flux control block is nothing but it is a circuit which can produce a voltage based upon the value of the frequency with the help of this graph. If the frequency is less than the rated frequency, the proportional voltage signal is given to the converter. So how much voltage signal we are giving here, how much frequency we are giving here, the same amount of voltage and frequency is generated by this converter, which is given to the induction motor, so that the motor will be rotating below the base speed, because here we have taken the 40 hertz. If we take the rated frequency is a 50 hertz. Not only that, it maintains the V by F ratio is a constant. Now we change this reference frequency to the 60 hertz. Now the frequency will be changing slowly from 40 to the 60 hertz in this manner because of delay block. So the signal also will be applied to the flux controller. The proportional voltage is generated here, signal that is given to the converter. So this converter is proportionally applied a voltage to the induction motor. If this frequency is less than the rated frequency, then V by F ratio is constant. Suppose if this frequency is more than the rated frequency, the voltage is constant at a rated value. So the maximum torque development in induction motor will be decreases. In this manner, the block diagram of variable frequency control of a three-phase induction motor is operated. Now we are going to see the some of the important applications of a V by F control type. Generally, we are using underground and water operated installation. Then we are going for the V by F control. Moreover, the application requires a explosive and contaminated environment such as the mines and chemical industry. In mines and chemical industries, more amount of contamination in environment that is going to affect the motor. In such a case, we can use the V by F control. Conventional method, we use the DC motor. DC motor can be replaced with a V by F control of a squirrel cage induction motor. It is very robust for the, this is the chemical industry, this is a mines. Traction system, this is one of the medical applications where we are using a V by F control of induction motor drive. Next, mill runout tables. This is a mill runout tables. It is also operating on a V by F control of a DC drive. Steel mill. Steel mills also we are using a V by F control of a DC drive. Compressors. Compressors also we can use a V by F control of a DC drive. Spindle drive also, it is also operated with a V by F control drive. Conveyor belts, machine tools, pumps, fans and blowers. These are the different applications where we are using a V by F control of a squirrel cage induction motor drive, which is exactly replacing the conventional DC. In this manner, there is numerous applications are there for the V by F control of a squirrel cage induction. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel, so that I am always available to answer all your